is, where's the names of the committee?
Oh,
Dave Smith and Badal,
it's right there.
Matthias, who is astrally present, and myself. So the first question we need to sort of as a committee decide is, the comprehensive exam answers have been provided. Do you want to discuss them now, or should we just discuss them along after the proposal presentation is over?
After it's over.
After it's okay? Okay. So is that fine with you, Matthias?
Yeah.
Okay. So then, so Kartik, you can go ahead and do your presentation.
Okay. Okay.
So sorry, one more question. So how long is the overall meeting supposed to take?
5 hours.
Normally 5 to 6 hours. But then remember it's just West Coast time. So no, I think he had
About an hour.
About an hour is his presentation, and then depends on how much how many questions in the middle. Normally it's anywhere between 1.5 to 2 hours. Total proceedings is about 2 hours plus, I think.
Okay. I have a meeting at 2:45 with the dean. That's why I'm asking. So I have to go to that.
Okay.
But that's 2 hours.
Yeah,
Okay.
That's 2 hours.
That'll be fine. And then if you are about to, I think by that time we'll certainly be already in the closed session. So at that point, if you need to leave, you can always just tell us.
Okay. All right. Very good. Thank you.
Okay.
Okay, all right, thanks. Okay, thank you, Rao, and thank you all for coming today. I'm Kartik, and the title of today's talk is Planning Challenges in Human-Robot Teaming. I'd especially like to thank the members of my committee for taking time out and being here today. So, human-robot teaming is becoming an important problem in daily life as we have more deployed robots. We are increasingly seeing that we need these robots to team up with humans and collaborate with them. And of course, human-robot teaming itself, the larger problem, it requires a lot of different technologies. So it requires things like perception, actuation, dialogue and communication between the various agents. And the thing that I'm going to focus on in this talk, planning. And in specific, this is important because right now, a lot of deployed robots, a lot of robots that are out there as applications right now, they're nothing more than glorified remote operated sensors. So what I mean by this is that there is right now a spectrum in the robotic technology that's been deployed. So on the one hand, at one end, you have these robots that are sort of completely remote operated by humans. So you can think of robots like drones, for example. Drones are robotic agents. But the truth of the matter is that there is a human who is sitting in a base somewhere, and he or she is completely operating this drone. And they're just being used for their sensing capabilities. On the other end of this spectrum, you have robots like your Roomba vacuum cleaning robot, which sort of can be called completely autonomous in the sense that it plans for its own, it does its own path planning and so on, but it doesn't really interact gainfully with humans. It doesn't really do any interaction with humans. So one of the keys to support this notion of sort of flexible human-robot teaming is to have automated planning on the robot. So you want the robot to be able to plan for its own goals, and you want it to be able to generate plans to achieve those goals. And flexible human-robot teaming is important because you have constant changes in application scenarios. So in this talk and in the thesis, I'm going to present two broad aims, two broad goals that I set for myself. The first contribution is the engineering of an effective integration of existing as well as novel planning technologies into a human-robot teaming system, into a human-robot teaming architecture. So that's the first contribution or aim of this talk. And the second one then is, once this integration is done and once you have it working on a human-robot team, to actually take a step back and analyze some of the design trade-offs that were used while doing this integration. So for example, was it reasonable to use a particular method? Are there other ways of doing something? And so on. So this is roughly going to be the outline of the talk. So like I said, coming to the contributions, the first one is the engineering approach that I'm talking about, which is that planners have so far not really been used in these human-robot teaming scenarios. So one of the main contributions then is to introduce an automated planner into an architecture for human-robot teaming. And as part of this, I will get into 4 specific automated planning methods or techniques that I had to use and extend to support this. So these techniques, very briefly, are replanning for a world that keeps changing. So obviously, if you're in a dynamic scenario, your robot is executing in a dynamic world, it keeps changing. The second thing that I'll talk about is this notion of quantified goals in an unknown world. So the world is not completely known, and you have goals that you have to achieve in that world. The third one will be model change. So what happens when your robot is executing in the world and there are changes to the model of the robot? How do you gracefully handle that? And finally, I'll talk about some work that we have just started doing that I'm quite excited about. This notion of using belief modeling of the other agents in your scenario in order to enhance the planning process further. And like I said, sometimes the first solution that we came up with in order to integrate the planner into the existing human-robot teaming architecture was somewhat ad hoc. It could be seen as, we were just trying to make the system work first. But then, in order to alleviate some of that, the next step that I took after doing the integration and after achieving this integration was to step back and do an analysis of some of the trade-offs involved in some of these solutions. So that's kind of the broad outline that I'm going to talk about. Now, since I'm talking about this engineering approach first, I should give you an overview of the integrated system as I'm talking about it. So in this integrated system, you essentially have the human and the robot, obviously, because they're trying to team together. And in the middle here, you have this overall integrated system that controls them. Now, in fact, this is a schematic from the DIARC integrated architecture system, which was developed by Dr. Schultz's lab, and we've been collaborating closely with them on it. Now, if you notice, the planner is actually a part of this integrated system, and so one big contribution of my work and my thesis was actually in situating the planner over here and managing the various issues that we had to consider when doing that. So if we zoom down a little further into this, what you see is that this box over here, that's essentially the planner component. And you can see immediately that the planner component gets input from the rest of the architecture. This input can be of various forms. So I'll go into this in more detail, but the input is generally in the form of updates to the world, to the goals, to the model, and also to the beliefs that you have about other agents. And the role of the planner is to send out a plan. So basically the planner needs to gracefully accept all of these updates in the world, and it needs to keep sending out a new plan whenever necessary to the rest of the architecture so that the robot can execute that new plan. So just to reiterate, the role of the planner in this. So again, this is the goal manager, and that communicates mostly with the planner. So the planner's role in our architecture is fourfold. So first, it needs to gracefully accept updates from a constantly changing world. So, excuse me. So obviously, when you have new facts that come up in the world, the planner needs to learn how to accept those. The second thing is to accept information on these goals, and sometimes goals may be on unknown objects, because obviously we are now dealing with a real world scenario where not everything is specified to you up front, and so you need to equip your robot to deal with this. The third one is this question of model updates. So you start your robot with a model of the domain physics of how to execute in the world, and then if there are actually updates to this, how do you handle those updates? And then the fourth one, of course, this work that I'm going to talk about towards the end, is about modeling the beliefs and intentions of other agents. And the role of the planner is to accept all of these and to generate a new plan to execute. And anytime there is new information along any four of these axes, then the planner needs to consider that information and replan if necessary, and send its new plan back to the architecture. Now, here's a short video that should give you an idea.
You can order to listen for instructions. Go to the end of the hall and try to look for a red box.
So that's the robot over there. It's executing completely autonomously in this world. It's in contact with a human teammate. I sped this video up a little bit. So basically there's a dynamic world. The robot is detecting doors on the fly and adding them to its world state. And there are goals that it's trying to achieve. And also, the robot has...
To go into a room when you are at a closed door, push it 1 meter.
So this is a model update that was given to the robot, and this comes in during the execution. So the idea is that the human tells the robot now that there's a new action that you can perform in the world. You can actually push closed doors in order to get into rooms. The robot didn't know this previously. So if you noticed previously, it skipped a closed door. But now when it sees the next closed door after this new action, it actually realizes that it can try to go into the room. And it does that. It uses the new action. So basically the planner has already replanned. And in this case, it sees a goal that it has to report.
There's a red box in room 1.
So that model update actually helped the robot to reach one of its goals, and without that update, it wouldn't actually have been able to do this. So this is kind of representative of some of the human-robot teaming tasks that we undertake. There are more complex tasks, there are simpler tasks, but this is generally how it works. You have a robot and you have a human who is in communication with that robot. So to go into the specific details of the planning tasks, and the rest of the talk is actually going to be about these tasks that I'm going to outline. The first one was replanning. So how do you handle updates to your state and to your goals in a changing world? And more importantly, how do you do this while you're executing? How do you do this real time? So obviously, because your planner is controlling the robot, you can't just stop the robot while it's executing and say, okay, you know what, I need to go back, assimilate all this, think about it, and come back to you. You need to do this really fast. The second thing that I'm going to talk about is this notion of open world goals. So basically provide a way for humans or other interested agents to specify quantified goals on objects that are not known yet in the world, on unknown objects. And once you have that, how do you actually handle these unknown objects? There are two different ways of doing this, so I will talk about that in more detail. The third question that I'll consider is this question of model updates. How do you accept changes to the planner's domain gracefully? And how do you do this via natural language? So you want to make it natural for the human. You don't want to have the human sit at a terminal and specify commands. You want them to be able to talk to the robot. And finally, this idea of belief modeling. Can you use models of the other agents in order to improve your planning process? Can you make your planning better? So I'll talk about that briefly towards the end. Now, before I move on, this is a list of publications relevant to this work in specific. Our work has been published in a lot of venues. There's been a significant amount of interest, like I said previously, in human-robot teaming and planning for human-robot teaming. A lot of this work has been done in collaboration with Dr. Scheutz's group at Tufts, the HRI lab. And I also want to acknowledge my other collaborators. Dr. Dave Smith is here, Jay Benton graduated last year, Paul Schermerhorn, and Gordon Briggs, who is currently at Tufts University. So moving on, so the first thing that I will talk about is the question of replanning. So the question comes up, why replan at all? Why do you need to replan in a world? Now, obviously, the reason for that is when you're executing in a real world scenario, you have new information that's constantly coming to you. Now, this new information can come from two sources. It can come to you either from the robot's sensors. So we know that the robot has many sensors. The job of those sensors is to provide the robot with new information about the world. And it can also sometimes come from the human teammate. So the human teammate can actually tell the robot that, hey, you know what, I know this new fact about the world. What can you do with this fact? And things like that. There's also new goals. So humans can always specify new orders. For example, they can give the robot new goals. They can redact existing goals. So they can tell the robot that, hey, you know what, I don't want you to do this anymore. Try doing this other thing instead. So we want to be able to handle that. And then in multi-agent scenarios, for example, you may have requests from other agents. So consider maybe you have two rovers, right? One rover can actually communicate data back to base, and then the other rover has some scientific equipment that it can use to analyze some soil. And so you might have requests from one rover to the other saying, hey, you know what, I have the results of an experiment, can you communicate this back, and so on. So there's new goals as well. And the requirement of a replanning technique that would work is essentially that it should generate a new plan that works in the new state of the world. So whatever updates have come into the state of the world, it needs to work in those. And it also needs to achieve any new goals that have been specified or any changes to the goals that have been specified. So how do we replan? Here's an engineering approach that we tried out. So essentially you can say that your planning problem changes from IG. So I over here is the initial state, the state where you started planning from for the robotic agent. And G is the initial set of goals that you were trying to achieve. And it changes to I prime, G prime, where I prime is the new state of the world, with all the updates assimilated. And G prime is the new set of goals, if the goals have been changed, if there have been new goals, and so on. So one idea is basically, as soon as you get these updates, immediately stop executing the current plan that you're executing, because the world has changed, and this plan might no longer be the best plan to execute in that world. So stop execution of the old plan by.
Kartik.
Yeah, Matthias.
Is it okay to ask questions?
Yes, please go ahead.
When you say stop the old plan, what do you mean by that?
So when I say plan first, right?
It's not running.
I'm sorry, go ahead.
The planner is not running to execution. What do you mean by that?
Right. So what I mean, I should clarify here. What I mean by stop the old plan is I'm concentrating specifically on the planner side of things. So what I mean is that the planner should know now that the old plan is no longer valid and it needs to start planning for a new process. We're not stopping the old plan on the architecture. The architecture continues to execute that. But the idea is that we want to make the replanning process fast enough that there isn't too much of a gap between this old plan and sending out a new plan to the architecture. Did that answer your question?
Yeah.
Okay, all right, okay.
I mean,
Yes,
you
Shiva.
figure here,
Yes,
so the output of the planner is new plan to execute,
yes.
and the architecture is executing.
Yes, they
so
are.
all you have to do is don't give a new plan. You can do whatever you want here,
Uh-huh.
as long as you don't give a new plan to the executor.
Right.
The executor will be executing the old.
Right. It will continue executing the old plan, and then when the planner comes up with a new plan that it thinks is better, then it will push it to the executor. Yes,
So
that's.
you don't have to do anything.
No. Essentially, not.
You don't
not
stop
not-
anything.
Yeah,
You
yeah.
don't stop
I was just outlining generally what happens. Yeah. So this step doesn't really need to do much. So the second step is to assimilate. So this is about the planner in specific. I'm talking about the planner component. The second step is to assimilate the changes in the state. So basically go from I to I prime. There is a minor challenge here of how do you specify those changes? How do you specify updates to the world? And how do you assimilate them? So I will talk about that in the next slide. Similarly, you also assimilate changes to the goals. So if you have a goal, you have new goals being specified or goals being redacted, you want to accept the changes to that. So you come up with a new set G prime. And you give this new instance I prime and G prime to the planner. So the planner essentially computes a new plan given this. And you send the new plan, once you have the new plan on the planner, you send it out to the architecture as Chitta was just mentioning, and you start executing that new plan. And we have an existing planner that can do replanning. So we use the SAPA replan planner, and you just use this technique essentially in order to replan. Now, the one issue that I was talking about. Yeah, sorry.
So the 1 and 5 steps are not really planner's job.
Yes,
Stop
so
execution or execute the plan.
that is the executive's job. Yes, that is the architecture's job. I just put them in order to give a better idea of what. Yeah. So essentially, the planner is doing 2 through 4. Yes. So one question here is how do you specify the changes in the world? An idea is to use an update syntax. So you can have this syntax that you use in order to provide new information to the planner. So in our case, the update syntax for SAPA replan looks somewhat like this. So U is an update, and an update is made up of these 4 components. So O is a set of objects or a set of constants. These are any new objects that are being defined that need to be added to the planner's representation. E is a set of new events. So it's a set of new logical predicates about the world. So these predicates can either be updates to the current state. So for example, obviously my planner state of the world is in terms of logical predicates. If there are updates to it, I specify them in terms of these logical predicates. Gn is a set of new goals that are being added possibly. And T is the current time point. So T is telling you when that update arrives. So you're telling the planner that the update arrives at this given time point. So an example of an update, updates basically look like this. Like I said, there are 4 main components. You can see those 4 over here. So you have new objects. So in this particular update, a new object room 3 is being defined, and room 3 is an object of type room. So it's an object that's being defined. There are 3 new events. So essentially you're telling the planner now that the robot is no longer at room 2, that it's actually at room 3, and that it has visited room 3. So these are the things that you're updating the state of the world. And all of this, obviously, all of this information comes from the architecture. The architecture is informing the planner that this is what has happened in the world, and you need to update your state of the world to reflect this. And then there's a new goal in this case. You need to have visited room 4. So this is how updates are specified. We take these updates, we assimilate them into the planner, and then we produce a new plan. I just outlined that in the previous slide. And this approach seems to work. I mean, we wrote about this approach. A lot of people have actually talked about this approach. And in general, it just works. It works with the planner, and we're able to integrate the planner with replanning into the integrated system. But this is an engineering approach. So after getting this to work, I actually took one step back. And I decided that what I wanted to do was actually understand the design trade-offs involved in replanning. In particular, I wanted to see, is what I am doing the only kind of replanning that is around, or are there other kinds of replanning which are used for other problems? So I actually took a step back and did a bit of research on this and came up with this. So obviously this first technique, the first model, replanning as restart or replanning from scratch, that's what we are doing in the previous case. That's what we're doing currently in the system. So what you do in replanning as restart is you discard your old plan pi. So I was just telling you about that, where the planner tries to come up with a new plan. There are no constraints on the planner while replanning, so it can just come up with a new plan. The only thing is that it needs to assimilate the changes in the world. Once it does that, it can come up with a completely new plan. And this technique is actually quite popular in communities like path planning, for example. So if you're doing just path planning for a robot, then if you see an obstacle in your path, then essentially what you do is you say, okay, you know what, there's an update now, there's an obstacle in my path, I'm just going to create a new plan to get around it and go on to my goal. The second technique is replanning as reuse. So the idea in replanning as reuse is that you want to minimize the generation burden on the planner. So you already had the planner do some work in order to generate a plan. Now the world has changed. Can you actually reuse some of that effort that you have put in order to generate the new plan? So that reduces some of the regeneration burden. And one of the ways of reusing some of this information is to try to minimize the differences between the old plan and the new plan. So essentially what you have is you have an old plan that's no longer working or no longer optimal for the state of the world that you're in, and you're trying to come up with this new plan. How do you do that? One way is to actually try to minimize the differences between these two plans. So you reuse some of the effort that was used in generating the old plan. And finally, the third approach to replanning is replanning to keep commitments. So what this means is you essentially start looking at the plan, the old plan pi, to see what it was achieving or what it was promising to achieve in the world before it was tragically cut short. And the idea then is that whatever that plan was promising to achieve can be seen as the commitments that are created by that plan in the world. And these commitments may either be to other agents. So for example, if you have a couple of rovers planning and one rover tells the other rover, I will communicate this data for you, and then that rover has to replan, that's a commitment to the other agent that it needs to consider, that communication commitment now. They can also be to specific metrics or to specific conditions. So you can have plans that have conditions for validity or preferences and so on, and you can have commitments to these metrics that you need to keep. And the idea in this particular approach is that you take all of these commitments and you try to project it down into the planning problem of the agent, and that's your replanning problem. You essentially do replanning that way. So a quick example to highlight all of these. So you take the rovers domain, since I've been talking so much about rovers, and so here are two rovers. You have rover 1 and rover 2. Rover 1 is equipped with some scientific analysis equipment, and rover 2 is equipped with some communication equipment that it can use. And here's a rock. So this rock can be observed, and you can also collect some soil samples around that rock. And you have a base station that can be communicated with. So you can send the results of observation or experiments to that base station. And the goal of this problem is essentially that you want to have collected the sample and you want to have communicated that sample back to the base station. And you can essentially start planning for this problem, and you can come up with a plan. So you can say that since rover 1 has the ability to carry out scientific experiments, I'll send rover 1 to the rock, and I'll make it observe the rock and collect the soil sample. And then rover 1 is going to hand over the results of that analysis to rover 2, which is going to communicate them back to the base, because rover 2 is the rover with the communication capabilities. Now, the problem, of course, is when rover 1 is executing, it's trying to execute this plan, trying to get to the rock, it hits an obstacle. It sees something in its path that it's not supposed to, and now there is an update to your world state. Your world has changed. What do you do, right? So think back about the three different kinds of replanning that I was talking about, okay? So the first approach, the replanning as restart. So rover 1 can essentially just say, oh, you know what, there's an obstacle in my path. Something went wrong in the world, something blew up. I'm going to come up with a completely new plan and start executing it. Maybe it had some other goal, observing some other scientific observation. So it just goes on to that. It forgets about what it had to do previously. The second approach, the one about reusing as much effort as possible, for that you can actually say that rover 1 can try to go around this obstacle and get back on track to its old plan. So it can say, I'm going to try to go around this green alien, and I'm going to try to get back to the rock and proceed with my old plan as possible. The third approach that you can try is you can actually label now the drop-off between rover 1 and rover 2. where you're exchanging the results of that experiment, you can explicitly label that as a commitment, okay? Because that's a commitment from rover 1 to rover 2, okay? And the reason that it makes sense to label this as a commitment is that now we are able to actually explicitly compare the cost of violating such a commitment, right, against the reward for actually, just staying and taking a picture of the alien. So for example, suppose the rover had a specific time window in which it had to perform this experiment, and if it actually stays and takes a picture of the alien instead, that time window is going to pass, that opportunity is gone, right? So now the robot needs to weigh these two against each other. It needs to say that, okay, on the one hand, there's the reward for taking a picture of the alien and sending it to base. On the other hand, there's the commitment that I made to rover 2 to send it this experimental data. And the reason that we want to explicitly think about this as a commitment is now we can compare them. It's no longer apples to oranges. You can compare them both in terms of the same metric, and the planning process can choose whichever one is the better thing to do. So
Kartik,
yes.
one sec. The assumption is that you know about aliens, right?
Yes, the assumption is that there is a defined reward on getting a picture of the alien, yes.
What if you don't?
Well, if you don't, then it's hard to do that analysis. Yes, you need that information beforehand for the planner to be able to do that analysis. Yes.
No, but I guess the question is this, we've talked about this before.
Mm-hmm.
What if there's something where you cannot put a reward on, right? Because you don't know what it might be.
Mm-hmm.
But it's interesting, right? I don't know, it detects water on the way, right? That's
right.
interesting, but...
Right. So it's harder to deal with things that you cannot quantify completely for the planner in general right now, because the planner essentially at the very core, it has to reason with numbers. It has to basically say that this is worth so much, whereas this is worth so much the other quantity, right? And it has to compare these quantities. So right now we don't really have a way of handling that sort of thing, but I think the planner can definitely be extended in order to take this notion of interestingness into account. But that's something that may have to be done in the future.
Yeah.
Okay.
Kartik, I have a question.
Yes.
A little more basic.
Okay.
So with the alien example, are you saying that in the first method, the replan method, it would not have considered taking a picture of the alien in its replan?
It could. It might consider taking a picture of the alien, but then the problem is that it doesn't really think about the commitment. So in this case, because I gave you the alien example, it's obvious that you want to take a picture of the alien rather than do the science experiment. But suppose this wasn't an alien, okay? Suppose this was some other rock, okay? Now these are comparable quantities, right? Because experiment at this rock versus an experiment at that rock, you really want to trade them off, right? You want to see which experiment is more valuable. And so the general idea, I use the alien as a sort of exaggerated example to show you that commitments are important. But I think the more important message from this is to actually label this thing explicitly as a commitment in order to be able to compare the two and to see which one you should actually be doing. So, okay. So anyway, so those are the three types of replanning, and I want to talk now briefly about the constraints associated with each type of replanning. So yes.
Which is your plan?
So this is the approach that we use currently,
Okay.
but then all of this is my analysis as well. In particular, I'm going to talk about something that we did in the next few slides. So this is work that I did with Dave, and we are actually also in the process of doing some more work on this. But this is what we use right now for the engineering part, for the integrated system, because that's what actually satisfies this, because the goal is to come up with a new plan quickly, and because you're doing it on a real-time robot. So this is what we use for the robot right now, but I have done some analysis on this part as well, so I'll come to that. So replanning constraints. For the first one, for the first approach, replanning as restart, there aren't really any constraints like I showed. You just get the updates from the world and then you start replanning. For the second one, for replanning as reuse, remember that I said for replanning as reuse, what we're trying to do is we're trying to start from the old plan pi, right? And you're trying to minimize the differences in the between the old plan and the new plan. So one idea is you can consider notions of syntactic similarity. So things like action similarity, right? So given two plans, pi and pi prime, you can compare them in terms of the actions that are present in those plans, right? And what you try to do is you try to minimize the difference in the actions that are present. And you can also do a slightly more complicated analysis like causal similarity. Now, causal here stands for causal links. So all plans are sequences of actions, and there are causal links between these plans because obviously one action in a plan may be providing an effect which is needed by another action in the plan and so on. So that's what I mean here by causal links. And finally, when you come to replanning in order to keep commitments, what you have now are you have dependencies between the old plan. So as an agent, when I had my old plan and the world changed, there are dependencies that were introduced between that and the other plans of other agents and so on. So what you want to do is project those commitments down into constraints that the new plan must fulfill. So any new plan that you make, it must also try to fulfill the old constraints, the old commitments that the old plan was promising. And an example of this obviously are the multi-agent commitments. I just talked about it in the case of the rovers. So just as there are three different, two constraints and three different models of replanning, there are also three different solution techniques. So replanning as restart, the one that we're using right now on the robot for the engineering approach, you can just use classical planning techniques for this. So what that means is essentially once you have the new instance I prime G prime after assimilating the changes in the world, you can just solve that with a classical planner and come up with this new plan pi prime. So that's done. The second one, for replanning as reuse, one approach that has been very popular in the planning community and that has been used quite a lot is this idea of iterative plan repair. And so the idea here is that you start from the old plan pi and you try to minimize the differences between pi and a candidate replan pi prime, okay? And you essentially find the best plan that satisfies I prime G prime, and the best plan is defined by a notion of minimizing the differences. And finally, when you're trying to replan to keep commitments, this is something that we thought about. This is part of our contribution in this paper. So we said that when you have these commitments can actually be seen as constraints on the plan generation process. So in essence, what they are their additional goals that your new plan needs to satisfy. So no longer do you need to satisfy just the original set of goals, but there's also a bunch of additional goals related to the commitments that you made previously that you need to satisfy. So these can be looked upon as soft goals, and I'll come to that in just a bit. So what happens is we compile these commitments into this set of soft goals GS, and then we add that set to the existing changed goal set G prime. So you get a further changed goal set G double prime, and then you just give this I prime and G double prime to a partial satisfaction planner, and you use the best plan that comes out of there as your replan. Okay. Now, I'm going to actually concentrate a little bit more on this technique from here on in on the discussion on replanning. So commitments in specific, as I said previously, all plans are made up of commitments, not just multi-agent plans. Even single-agent plans are made up of commitments. What are those commitments? They're causal commitments. So you have actions that are supporters and producers, okay? So a supporter is an action whose effect is actually supporting some other action further down in the plan, okay? And vice versa, a producer is an action which is consuming one of those effects, okay? And so this notion has pretty much been, it's been formalized in the field of partial order planning. There's been a lot of work on this. And obviously in multi-agent scenarios, you can have agents that enable or disable conditions for other agents and so on. And like I said, commitments can also be seen as goals. They can be seen as the most natural way of constraining change. So what I mean by that is that commitments obviously can model, having to commit to a particular situation. So if you had a drop-off commitment with another rover, you can model that as a goal. You can say that, oh, in the previous plan, I had a goal to drop off this sample to the other rover. Maybe this new plan needs to uphold that goal as well, okay? But you can also have commitment to form. So what you can say is, oh, in the previous plan, I actually had 4 actions. I had a communicate action. I need to have that action in this new plan as well. So that's a commitment to the form of the plan rather than what the plan is achieving. So you can have different kinds of these. And the idea is that both these types of constraints can be compiled into the same planning substrate, into the same planning technique, which is partial satisfaction planning. So I'll give you a quick example to make this a little more concrete since I've been talking in abstract terms. So consider a plan pi, which is just these actions, A, B, C, D in the following.
What may not be obvious,
yes,
just listening to you right now, is if you go back to the previous slide, this slide in essence saying that M2 and M3 can use the same technique.
Right. Okay, I'm sorry, yeah, maybe.
Because you made it sound as if each of the methods have a separate technique, but
right,
then you are going on to argue that really the technique for handling M3 is general enough to handle pretty much everything.
Right, so yeah, that's right. Rao is actually right. So what I am saying actually is that the technique that I am going to show you for handling M3 using partial satisfaction planning, I'm actually going to show you a compilation that shows that this is general enough to handle M2 as well, to handle the other kinds of constraints as well. So that's the idea, and I think that's what Rao was clarifying. So so really quickly an example. So if you have an old plan pi of this form, then action similarity, and you have causal links between the actions in this plan, obviously. So A is giving B something, and so on. There are causal links. Then the new plan pi prime. So here, this is a plan that is maximally similar with the old plan with respect to action similarity, because it happens to have all of the actions of pi and no other actions. So there is basically no difference in terms of the actions present. Okay. And when you're talking about causal similarity now, it's no longer enough just to have the same action. So causal similarity is a slightly stronger condition. You also need to preserve each one of these causal links, okay? And any difference between these is counted as, one difference, and you penalize it that way. So one compilation, this compilation that we came up with for action similarity to partial satisfaction planning. So like Rao said, this is showing that M2 can essentially be compiled into M3 and then solved, okay? So what you do is, say, for every ground action A in the old plan, okay, you create a commitment constraint to have that action in the new plan as well, okay? So remember, M2 was this technique where you're trying to minimize the action differences between the old plan and the new plan. And so what you're saying is that you want to create a commitment constraint to have that old action in the new plan as well, okay? And the way we do this is you create a predicate, A executed, along with the parameters of A. So when I say parameters, I actually mean ground objects, okay? And you make a new goal on A executed. So essentially what you're saying is, here's a logical predicate, okay? The presence of this predicate as a goal means that you have to have that old action in the new plan as well, okay? Except that we don't really say have to have, we relax that notion. We use soft goals instead of hard goals. So we say that if you have that old action in the new plan, we will give you a unit reward, okay? And if you don't, then there will be a unit penalty to this. So this is kind of partial satisfaction planning. You have to, the planner has to do the trade-off. And every goal thus generated in this step is added to make this set G double prime. So as an example, if you think about the previous plan, which had 4 actions, right? So you would essentially generate 4 goals, 1 for each action, and you would add that to this set to give you G double prime. And then you give this I prime and G double prime to a PSP net benefit planner, and you return the plan that has the highest net benefit as the replan, the new plan pi prime. So that's how you compile action similarity to PSP, and the full details of this compilation are in this paper that I mentioned. You can also compile causal similarity to PSP in a very similar fashion, except now because it's a causal structure that you're talking about. It's no longer just the plan, but you need the causal links as well. So you can do a regression analysis in order to extract the causal structure of the plan pi. And then it's a similar approach. So now instead of every action, for every fluent of every producer or consumer. So these are actions that are either giving effects or consuming preconditions, because we are now at the causal level. We're doing a causal analysis. You create a commitment constraint, and then you add all of those goals again, and you do the same thing. You solve it using a PSP net benefit planner. And again, like I said, the details are in this paper. I'm happy to talk about this further if needed. So just in diagram form, to make it a little more concrete, suppose you have this action A, okay? And A was in your old plan. So A has some preconditions and it has some effects. So A is the same for both action and causal similarity. For action similarity, your compilation would be the following. So you create a copy of A called A, action similarity. You have the same preconditions and the same effects, but you have an additional effect now, which is A executed. So essentially what you're saying is that A executed, you have a goal on that in your new planning problem, and you're saying AAS is the only action that can give you that effect. So you're essentially forcing your planner to include this action in the new plan. And similarly for causal similarity, it's slightly more complex here because you are now reasoning about the causal links. You're no longer reasoning just about action presence, you're reasoning about causal links. So this is the analysis that we have performed so far. Now there is some work that can be done to extend this, so I'm going to talk briefly about possible proposed work for this. So one idea is that you can cast replanning constraints as plan preferences. So one of the ideas here obviously is that when you have a new plan and you have a process for generating that new plan, what you're telling the planner is that I would prefer to satisfy the commitments that the old plan was satisfying, or I would prefer to have the same actions that the old plan had. So these are actually just preferences if you think about it, and it's been shown that simple preferences are in fact the same as PSP goals, as soft goals. There is work on this. qualitative preferences actually allow us to go a little further. They allow us now to specify not just goals of achievement, they also allow us to specify more complex constraints, so trajectories on a plan that is generated, okay? So you can have things like eventually the following condition should hold, eventually the following formula must hold, and so on. So that allows us a little more expressivity. And it also enables the use of many fast planners because preferences has been explored quite a lot in the planning community recently. And the second task that I am proposing for this particular part is to extract state commitments from any given plan pi. So remember I was talking about commitments throughout the past 10 slides or so, but then the idea is who is giving you these commitments, right? It's reasonable to think that humans might tell you that a following thing is a commitment, but you also want an automated technique of extracting all of the commitments made by a previous plan, okay? So that's the other thing that I propose to do. And the anticipated approach is, for the first one, for simple preferences, we already have a compilation from commitments to PSP, to soft goals, and we showed that in the paper that I mentioned. And then Jay Benton has done some work on compiling soft goals to simple preferences. So there's a fairly straightforward compilation between these, and I intend to actually make a method that will do this formally. So that's the first approach. And then as far as extraction of commitments goes, we can actually do this in a fairly intuitive way. So given your old plan pi and given the initial state of the planning problem, as well as the domain description, so all of the actions in your available to you, what you can do is you can start from I and reconstruct the state space corresponding to the plan pi, okay? So what you do is you start in the state I and you successively apply all of the actions in the old plan, and that will give you a state space graph. It will show you the state space that that plan was going through, and you essentially store that state space and you pick some predicates from that and label them as commitments, okay? So this completes my discussion of the replanning part of the work. If there are questions, yeah.
So what's your conclusion? Like there are three, M1, M2, M3?
Yes.
So basically you say M3 is generalized
Yes.
enough and it covers...
It can model M2, it can model M1. So M3 is general enough to model all of these. And I want to actually extend M3 a little bit with some more.
Okay, if it's so general, it must have something, some costs there.
Yeah,
What
so
is
the
another cost?
right. So the cost there is that it takes you a longer time to actually reason with all of this information about commitments, about net benefit, and so on. Now, of course, that argument will fall through eventually because you will have planners that get faster and faster. So when you have PSP planners and then these preference-based planners that I'm talking about, they will get faster and faster. So at some point, I think the aim is that I will be able to use the techniques of M3 and substitute them on my planner. So instead of just using M1, which I'm doing right now in the integrated system, my ultimate aim is actually to use a planner that supports M3.
But also you said that it works.
It works, but then I want to be able to specify.
Why bother them?
I want to be able to give humans the opportunity to specify more complex things. So you can specify preferences, you can specify commitments.
No, but you haven't showed us it didn't work yet.
Not yet, but that
There's
is
no need for you to.
right. There's no need to do it right now because it just works in the engineering approach so far. But wouldn't you agree that you want a planner? If you have a planner that's controlling a robot.
I don't know. I probably want a fast planner.
Yes, but my point is when planners get fast enough, right? So I'm not.
I don't know.
Sorry.
I think the argument that is missing that you could easily make is commitment sensitive replanning or structure sensitive replanning important when in the context of human robot.
Okay.
That is what he's asking, and I think you have the answer for that. So.
Right. So yeah, actually that is true. And so if you think about it, right, when you have human-robot teaming situations, right. So
That's a good point. Yeah. Otherwise, it's completely planning.
Right. So in human-robot teaming situations as well, that's a multi-agent scenario as well, and you do have commitment. So the robot actually publishes its plan when it starts executing to the human. It tells the human, okay, I am going to go and achieve the following things. Now, if something happens to break in the world, and it can't do that. So, for example, the robot says, I will go and look for humans in this room, and then you go into a broken building, right? And that room is blocked off now. What do, right? You need to come back and you need to renegotiate that commitment. So I think that's the point of actually having a more complex way to support you.
Could you back up just one?
Yeah.
So I also think your extraction of commitments here is a bit weak.
Okay.
You just say pick predicates and label them commitments, right? But some of these predicates that you're generating are just in service of your own plan.
Right.
Okay, as opposed to those that in fact have been perhaps communicated to another agent, right? And the other agent is relying on them. So saying that you can just pick these and label them as commitments, right? There's a deeper meaning to this that involves the other agents.
I agree with that. I think this should be changed. This should be corrected to actually say that we don't just pick predicates at random from the state graph. There are some predicates that actually reflect commitments to other agents, whereas some other predicates are just used for the plan, for the current plan that's being made just by this agent alone. So in a sense, there are some predicates that are of value to other agents as well, that have a meaning to other agents. That's what you're saying? Yeah, I do need to update it to take that into account. I think that's a good.
I think number 2, you're confusing the way you set up synthetic experiments, where you randomly pick some things and say those are commitments, just to compare methods with the reality. I don't know that in reality you can just look at the states I'm going through and say, oh, these must be commitments I made. That information comes separately.
Yes, but
I think the extraction of commitments, that whole method is not
no, but
right
would you
now.
right? No, but would you not agree that if I'm given the plan of the previous plan of an agent, right, the commitments are part of the state space of that plan?
That is fine. But
Yes.
there's so many things.
Yes,
For
yes.
example, I'm wearing this sweater. Was that a commitment?
Right.
To be, wearing this sweater for this particular proposal? No. I can't just randomly pick states. So I think that part is a red herring. You should just, if you extraction of commitments, if you want to do it right at all, you cannot do that. I think that one is coming from the way you set the synthetic experiments,
Right.
where you just had to say some commitments were there.
That's true. I do need some more. I think I need some more directed analysis in order to pick the actual commitments. I can't just say a throwaway thing like pick predicates. I do need some analysis over there, and that's right. I will update it to take that into account. Okay, so I'm going to move on quickly to the next part, which is dealing with open world quantified goals. So essentially, why are goals important? Why are they important to human-robot teaming situation, to a human-robot teaming scenario? So obviously, the utility in human-robot teams, it stems from the achievement of goals by the team, okay? And since this is a team, you have assignment of these goals among the different teammates, so among the human and the robot and so on. And the idea is that the robot must plan autonomously to achieve the goals that are assigned to it, okay? And that's why we need the planner, and because there might be like a complex causal cascade that needs to be performed in order to actually get to the goals that are assigned to the robot. And it may also include the optimization of some metric on the part of the planner. And in specific, I was interested in looking at this problem of open world goals that are assigned during the execution process. So the planner has planned, and then the robot is executing, and suddenly there's some new information that comes in from the world. How do you deal with this? And this is actually work that we published in the ACM TISC journal, and I'm going to detail that work now. So goals. In human-robot teaming scenarios, the bad news is that there are many unknown objects in the world, okay? So if you take, say, a search and rescue scenario where you have human-robot teams, you might have wounded humans in wrecked buildings, okay? And so these wounded humans, you don't really know about each human. You might know that there are wounded humans, right? But you don't know, for example, that person A is wounded or things like that. So there are unknown objects in the world. What's even worse is now you have goals that are specified in terms of these unknown objects, okay? So now you have a goal for the team that says, report all wounded people that you find. You don't even know which wounded person is in there, but you suddenly have a goal now on that unknown object. And really the worst part is that you don't even know how many of these objects there might be, okay? So you don't know if there's 1, if there's 10, if there's 100. So that's the idea here, that you have an open world, you don't know all the information, and you have quantification. So you have a goal which is that you don't know all the numbers of. So you have these things known as open world quantified goals. So one way of handling these one way of resolving this uncertainty is by using sensing, because your robot has sensors. It can go into the world and it can try to look for humans. So one way is to handle sensing. There are some extreme Yes.
So what is the goal here? It seems you are changing the goals all the time, right?
Right.
First is the wounded humans. You want to find the
Wounded humans, yes.
Second is you want to report. So you are adding goals.
No. The goal in the scenario is to report wounded humans. We need to find them in order to report them. The goal is report all wounded people that you find. That's the only goal that I'm talking about right now. Finding wounded people is in service of that goal. Obviously, you can't report someone unless you find them. So the only goal that I'm talking about is reporting wounded people.
But why then they are unknown objects? You already know.
No, you know that there are wounded people, but you can't say that there is wounded person 1 in room 1. Like, you cannot name the objects beforehand. So you have to sense in order to see if those objects are actually there. So that's the challenge that I'm talking about. That's what I'm going to talk about in this part. So there are some extreme cases as far as sensing is concerned. The robot can just say that, you know what, because this is a hard problem and there's too much sensing involved, I don't want to sense at all, okay? So it can just say, I will assume that what I know is all I know. I'm not going to use my senses, okay? But there is a problem with that in the sense that it will only achieve goals on predicates that the robot already knows. So, for example, these wounded humans, the robot would completely ignore them because it doesn't really know where the human is or that there is a human in the room until it actually senses, right? So if it does this under-sensing thing, then it's just not going to achieve any of those goals, okay? Now the robot can try to overcompensate for that, and it can insist on closing the world. So it can insist on knowing all the information in the world about all of the objects in the world, okay? But this is clearly a very infeasible approach because your robot will end up over-sensing, and also one important thing is because now you have quantification. So you were told something like report all wounded humans, okay? But you don't know how many wounded humans there are. There might be 1, there might be 10, there might be 100, right? And if you try to close the world, that's like a never-ending task. You might never be able to actually achieve that.
Right. Is this true that if I just find the 1, I satisfy my goal?
That's what we are going to show. We are going to go ahead and show that it's possible to set it up so that this happens. So that's the approach that I'm going to talk about. So one idea then is to combine the sensing and planning processes, okay? And in specific, use the planning to actually limit the sensing in some way, okay? So you have some information on these unknown and unenumerable objects, and you have goals conditioned on these objects. So what you want to do is limited sensing. You want the planner to direct the robot to go in and sense something, but you want to limit this in some fashion, okay? So that's what I'm going to talk about. That's what we had to do in order to get the integrated system working. Because remember, again, like I was saying, this is a real scenario. We had to actually implement it on a real robot. We had to test it out in a building, with rooms and all of that stuff. We had to find boxes. I mean, actually there was a case where there was a human lying down as well. So we had to do this in real time. So we had to implement this. So one way of implementing this that you can come up with is by asking the following questions, okay? When do you start sensing? That's the most important question. When should the robot start? When should it use a sensing action? The second question is, what do you look for? So what should the robot be looking for? Sensing is fine, right? But you need to know what it is you're looking for. So for example, what object type is the robot looking out for, okay? And are there any distinguishing properties of that object? Is there information about that? Can you take that into account? The third question is, okay, now that you've started sensing, when do you actually stop sensing? How do you limit your sensing, okay? So when does the planner know that it has enough information in order to act conclusively on the goals? And the most important question in some respects is, why should the robot sense at all, okay? Why should it sense? Is there an object that leads to a goal? Is there some reward that it's getting? Is there a bonus that it's getting for performing the sensing? Because if there isn't, then sensing actions have cost and they take time. Why should you do this? Are you getting a reward for it? So that's the fourth question, okay? And so in order to answer all of these questions, the approach that we came up with is the following construct. So I'll explain this construct in detail. What this is doing is, this is an open world quantified goal, and it is answering these 4 questions about the sensing. So in a sense, what it's saying is, when do you start sensing? So in this case, you're saying that for all objects of type room, so whenever the robot sees a room, then it needs to start sensing. So that's a quantified object. So you're saying that in every room that you see, you need to sense inside that room, okay? The second question of what do you sense for? So you want your robot to be sensing for an object of type person, okay? And additionally, that object might have the following properties, that that person might be wounded and that person is in that room R. So there are some additional properties about that object that you are sensing. The third question is, when do you stop sensing? So now the planner has actually put in a sensing action. It's directing the architecture to go out and do this sensing, okay? When does the planner know to stop? And so for that, we have this thing called a closure condition. So this is basically telling you that, okay, now I have looked in a room, okay? I've finished looking in a room. So this room is now closed with respect to my information. So I can stop sensing. I no longer need to execute sensing inside of this room, okay? And then finally, the fourth part of this is, why sense at all? Why is your planner, how is your planner going to tell the robot to sense? So the idea here is that there is a goal on wounded people, and that goal has some reward. It has a reward of 100 units that it carries with it. So your planner is essentially saying, I want that reward, so I'm going to send the robot in to sense, okay? So that's an open world quantified goal. The approach we use, yes sir.
I mean, it looks like half constructed plan. Means you were telling what to do rather than specifying what you want.
Okay, this is actually not a plan. I'm actually just specifying information about the object that it is sensing for. I will actually talk about how this information gets turned into a plan. But this is just information on that object. So all you're saying is that, so for example, if you were talking about boxes instead of people,
go ahead.
Right, and I mean, I think some background here also is that the planner is depending on the architecture to do like the object recognition, for example. So the planner is not slotting it into an object of type person or type door and so on. So we're getting that information. This is just a way of specifying that information.
Okay, can you just explain this again?
Okay, right, yeah. So this is essentially a construct to represent information about unknown objects to the planner, okay? So essentially what happens is this construct goes into the planner. So going in more detail.
No, just explain it in English.
Right. So it's basically you can think of it as a goal with additional information.
So you're saying for all rooms.
I see. Yeah. So what it's saying is that for all rooms, sense for a person in that room, okay, and that person should have the following properties, okay, that person is wounded, okay, and that person is in the room. So this is the person object, this is the room object, okay. And then what you're saying is you stop sensing when the following condition is true, when you have looked for that person in the room. So that condition comes to you as an update. You stop sensing at that point, okay? And the reason you need to do this is that there is a goal on this object, on the person. You need to report that wounded person as being in room R, okay? And you get the reward for that. Was that clear?
Okay. Yeah, I'm trying to think if this is a goal.
Okay. Okay. Yes.
So I have a related question. Just in what sense are these quantified facts and quantified goals? So you have you have the room is an unknown object, and you have for all, which I see as like a quantifier, and then the person is an unknown object. Is there some implicit existential quantifier?
Right. So there is actually, the quantifier is actually over the room, okay? So essentially what this goal is saying is that the presence of a room, okay, alerts the planner to the possibility that there might be a person inside that there might be an object of interest inside that room, okay? So the quantification is actually over room. So what you're saying is, for all rooms, like for all rooms that you see, you need to actually go inside and sense for an object inside that room.
So if you had a goal that was like for all rooms, look for this definite object, the red box. Is that also going to be a quantified goal?
That would be quantified, but then you would define that specifically in terms of an object. So if you said, well, first of all, how would that work? Because if you say for all rooms, right, and you're giving definite object identifiers, are you saying that the same object is in different rooms? I mean, because when I'm talking about identifiers, every object has to have a distinct identifier of its own to the architecture. So you can't, for example, have red box 1 both in room 1 as well as room 3. So I'm not even sure that.
Well, I was thinking if you didn't know which room it was in. I guess I'm just trying to understand precisely like what's being quantified over.
Okay, so it's being quantified over rooms, okay, but it's not a specific object that you're looking for. You're looking for the type of object, people, wounded people, okay, and you're not looking for, say, wounded person 1 versus wounded person 3. You're saying that for every room, check if there is a wounded person inside that room and report that person. That's essentially what you're saying.
And so for Juan's question, what if there's 2 wounded people in the room?
Right. So right. So right now we basically just handle. The planner would be able to handle only 1 wounded person being inside a room. But as I'm going to detail in the approach, we actually do a sensing sweep. So there is a possibility, if there are, for example, 2 wounded people, that the architecture will sense both of those people, and so it will create 2 objects to send back to the planner rather than 1. It can actually do that.
So going back to Chitta's comment, I think it's a very interesting comment.
Okay.
There is some plan knowledge that is present in the way you're specifying. The pure goal is it's a conditional goal.
Mhm.
The pure goal is for every wounded person, report the wounded person. That's the pure goal.
Right.
Okay, now the question of course is where do you find the wounded people?
Mhm.
Okay, the planner is not supposed to, if you are talking only about providing pure goals, the
Mhm.
planner would not be told where to find them. This goal
So the room
is essentially sort of think of this as like an HTN reduction.
Right, there's a
It's
D-
saying take the conditional goal, wounded person report
Mhm.
and convert it into look for wounded people in rooms and report.
Yes.
Okay, maybe there is another reduction too, that, for example, this allows the robot to avoid looking at the ceilings for wounded people.
Yes.
Which
Okay.
is very much possible, if all I'm saying is
Look for
wounded
wounded
person, look for wounded person, I don't know where the wounded people are.
Right.
So in that sense, actually,
There is some knowledge.
What you're doing is you're sort of directing the sensing by saying, rooms are where the wounded people will be, and
Yeah.
that is something that you're adding on top of.
Right.
So that's
Right.
a good point to you.
Yes.
I know that that's not the way it was written, but in fact, when you're talking about the conditional goals later on,
Mhm.
those come in the pure form.
Yeah, of the antecedent and
Yeah.
yes. Okay. Okay.
And also
Thank you.
probably don't need to add any ways to find one. Because as long as you find one, you already know you need to send someone.
Right.
Probably it's good enough, right?
Right. Yeah. Fair enough. I mean, if you report something, you
Right.
say a
That's the
human.
point. It depends on what you want to do for that particular rule.
Well, you send in your robot.
Yeah, but why would you want to agree with one now?
No, because he's talking about sending humans.
No.
He's talking about sending someone to extricate-
I understand.
Yeah.
But the point is, you still want to know how many people are wounded.
No, you do. No, I thought his point was basically, regardless of whether there's one person or 10 people,
Slow
you.
down. He is essentially undercutting the need for unquantified, objects. Okay, he's saying the moment you find one object that's good enough, and you're agreeing with that, in which case then this idea of
No,
open
no.
world quantified
That's-
goal seems.
No, that's not. Okay, I'm sorry.
That's what you agree with.
No, that's not what I thought. That's not what.
I don't have the hidden agenda, but I think it's practical. It's very
No.
practical
So the
from my point of view.
Okay.
Instead of counting people, you just count the number of rooms with injured people.
Okay.
I think it's better, right?
Well, no. I mean, you might also try.
Why should I care about?
No, you do want to report them because what happens later might be dependent on that, right? So suppose there's one injured person versus 10, the kinds of resources you need to send in to rescue those
Well,
people.
then you really have a problem with this, right?
Yes, with
you
this
don't
right now-
reward people you don't reward the robot with the reward.
With multiple people right now, yes. With this construct, yes. But just to answer your question, I think you do want to report more people eventually going forward, if there are more people in that room.
Is it better to report the rooms, number of rooms?
Right now, you're basically saying that if there is a person in a room, that's essentially what's happening. But there might be a situation where you want to actually say how many people there are in a given location, because that
Because
would.
the human robot teaming, right?
Yeah,
So
distribution of
I can ask him
resources.
now you count.
Right. So the distribution of resources might be affected by that. So yes, I think that's a very fair. Okay, so moving on to the solution approach for the open world quantified goals. So what we do is we provide the OWQG to the planner. So remember this in the previous slide. This is the OWQG that I'm talking about. So the goal as well as some knowledge, as Chitta pointed out. We provide that to the planner. And then the planner, what it does is right now it uses an optimistic determinization. Okay, so what it does is, given an open world quantified goal, it goes ahead and assumes the presence of the object. Okay, and it creates a runtime object. So in this example, for every room that the planner knows about, that for every room that the planner senses, it would create a runtime object, which is a wounded person inside that room. So I mean, this is just really a fancy way of saying that the planner kind of tricks the robot by saying, okay, you know what, there may be a wounded person, there is a wounded person, you need to go inside and sense. And this happens for every room. So that's what I mean by optimistic determinization, okay? And again, remember that here I'm just detailing what worked on the integrated system. I will come to an analysis of whether that's the right thing to do right after this discussion, okay? So basically you use the optimistic determinization and then you use the replanning theory from the previous part. So what you say is you give this new this information about the new runtime object to the planner, you give it an update, and the planner the planner makes a new plan that uses the runtime object in order to achieve the open world goal. So basically it reports the runtime object and it collects the reward, okay? So this can be seen as, so originally you had this flat search space, okay? And then you're now dropping the OWQG into this search space. The planner is creating an optimistic runtime object, it's dropping it there. So basically what you're telling the robot is that it's advantageous to go in here because you can actually report that person because that person has been created as a runtime object. And then once the replan is made, you send it to the architecture and then you execute that replan. And in specific, what we do here, so obviously you can't have wild optimism on the part of the planner. You can't just assume there are people left, right, and center and keep reporting them. So what we do is we execute the new plan up to the sensing action, okay? And the sensing action is associated with the closure condition that I was talking about, okay? So in this case, like a specific example of a sensing action would be look around the room, okay? Look around the room is a sensing action, and you know that look around the room gives you your closure condition, which was basically looked for a person, okay? So you execute your plan up until then, and you know that because it's a sensing action, you can then go ahead and delete that runtime object, okay? Because there are two possibilities. Either there was a human, like a wounded human, or there was no wounded human, okay? You delete the runtime object regardless, and if there was a human, then the architecture sends an update back to the planner and says, oh yeah, I really did sense a human, you need to alert people about this. If there was nothing, then there is no object. You don't report, you don't do any of those things, and you move on. So that's essentially the engineering approach, how that works. And an example of how this approach works. So here's a plan. You have the robot basically starting at the start of the hallway, okay? And the robot has a goal, an original hard goal, to deliver a medical kit to the end of the hallway, okay? So the robot comes up with this plan. It says move through the hall, get to the end of the hallway and deliver the medical kit, okay? While the architecture is executing this first plan, okay, you have this open world quantified goal that comes in. This is the same OWQG that I talked about previously, okay? So this is telling you that, in rooms there might be wounded people. So along with that, you get a new update because obviously remember, you're interrupting the planner, you're interrupting the architecture, you're interrupting the planner while the execution is going on, okay? So the architecture needs to tell the planner that, hey, look, here is the new state of the world at the point where I interrupted you, okay? So now what you're telling the planner is that there is a new object of type room 1, okay? And then the robot is no longer at hall 1, it's instead at the second hallway segment, okay? And that hall 3 and room 1 are connected. Now this is the architecture basically telling you that, I've used, say, the laser rangefinder and I've found these things, and here are these objects and here are, predicates that connect them, okay? And you're also saying that this is the current time point at which I interrupted your planning process, okay?
Yeah, so the architecture sent you this open world quantified goal.
Yes.
So does it stop or it continues doing what it was doing?
The architecture?
Yeah,
the architecture continues.
Like in the sense the executor or whatever.
Yeah, the executive continues executing this old plan until I, as the planner, interrupt it again and say, no, wait, here's a new plan, right? So in fact, there is the new plan. So this is an example of the new plan that comes up. So once this update is assimilated along with the open world quantified goal, the planner actually says, okay, you know what, I have a new plan, okay? So because this update said that the robot is at the second hallway segment, you start planning from that, okay? So you say move from hall 2 to hall 3, and now it makes you enter the room. Instead of going straight to the end of the hallway, it makes you enter the room and sense for this person, okay? Now this person here is the runtime object that I was talking about, okay? This is the object that the planner created, okay? And so in a sense, this object might actually exist only in the planner. It may not.
But how does this work? Since the architecture is already executing,
yes.
So by the time you make the new plan, it's already passed some.
Yeah, but the planning is fast enough. Actually, it's in the order of microseconds. So not too much has changed in the world before the new plan is sent out. It's a reasonable question that if the planning takes long enough, your world has changed and it is no longer accurately represented by this. But we have seen, in our empirical evidence that the planning is fast enough that this happens in the order of microseconds. So that's not a problem for the current system.
You can say almost it stops.
Yeah, I mean.
Is that what you stop in the very beginning?
If it doesn't affect, that means it stops. Right?
Yeah, it's the same as the how to replan, the first and the fifth step of that. It's actually the same question. Yes, I mean, it's fast enough now that
because if it doesn't stop, then it will change. So it will not work.
Yeah.
So
only
it works because
I am hesitant to say that it stops because it does not right now. It's fast enough that it doesn't need to stop. It can continue doing what it's doing, and that's the reality of how it's implemented right now. So it's fast enough to be able to deal with that. It's the same thing, yes. So, Okay, so it creates this plan. So if you look at this plan, there is a bolded part to it and a grayed out part. So the planner actually comes up with this entire plan, okay? But what we do is we only execute that plan up until the sensing action, okay? And the idea behind this is that when you sense in the world, you're finally resolving the uncertainty one way or the other, okay? And you can go ahead and delete this, runtime object. So we execute up until the sensing action, at which point there will be another update. An update like this will go to the planner, either telling it that there is a person or that there is no person. There's not going to be a new object. And then you can replan and continue on for your other goals. So this is the approach that we use on the system right now, and it works because of the optimistic determinization. So basically what I said was that it assumes the existence of the objects, but then it tempers that wild optimism that it has by doing some sensing. So it basically says, even though I'm creating the runtime object, I'm actually sensing to ensure whether that object is there or not before you actually end up reporting that object to the person. And it replans when there are invalid assumptions because it gets updates from the world. And this approach is slightly reminiscent of other existing planning approaches, in specific this planner called FF Replan. I'm actually just going to skip this because it's not really very relevant to the current discussion. So obviously one important aspect is that you need to have partial satisfaction planning. We talked about partial satisfaction planning a little bit when we were talking about replanning. It's important for this problem as well because obviously your open world quantified goals are actually bonuses, right? Because you're telling your planner, try to report as many humans as you can. So it's almost a bonus that your robot is going in and telling you that there are these people to be rescued. Additionally, the reason why why soft goals are important here is that there is quantification now, and it may not be possible to satisfy all possible groundings of an open world quantified goal. So imagine if you're in a scenario where instead of say 3 rooms, you have 100 rooms, right? So you're in a hotel lobby, right? And you have 100 rooms on either side, and you have a deadline to get to the end of the hallway. You tell the robot, you need to get out of the building in say 100 time steps, okay? Or you need to deliver this medical kit before 100 time steps. Then it's not possible to make plans to go into each one of those 100 rooms. So you want to make the open world quantified goals soft, so that the robot does as many as it can, given the metric constraints that it's subject to. And obviously the PSP does a net benefit analysis. It balances, on the one hand, the cost of sensing with the reward for actually reporting an injured human, okay? So, I mean, here's a quick evaluation of this on, can you see? Yeah, that's Cindy, our creepy lifelike robot. This is at Dr. Schwartz's lab, actually.
Cindy, Commander Z really needs a medical kit.
So that's your goal.
Does he be on the room you are in?
Okay.
Yes, he's in the room with the green door.
So that's.
It is a white box with a red cross.
So these are the properties of that object that you're sensing for. White box, red cross. And this was a really simple evaluation just to show that the open world quantified goal is being processed. It processes that, sees the object, has some trouble picking it up, but it picks it up. And it then regenerates a plan and plans to take it back to wherever the commander is. So that's just a quick evaluation of this. And obviously, like I said, it works, this approach that we're using, it works in the current system that we're using, okay? But then the idea is this really the best thing to do, okay? Given that what we're essentially modeling is we're modeling there's uncertainty in the world with respect to the presence of these objects, with respect to the presence of wounded people. So is it the best thing to optimistically determinize the entire world, to just assume that there will be people in each room? It may not be, because you may actually have some additional information about this uncertainty, okay? So you might actually have some probability on the distribution of these objects, right? So you might have some historical data that tells you that it's more likely that wounded people are often found in bathrooms than they are in kitchens. You know, maybe people huddle in a bathroom in the case of an earthquake or something like that. So there might be some historical data, there might be some probability distribution. Additionally, the idea is that your optimistic determinization is making the robot sense too much. So for every room that you happen to find, you will go inside, you will make the robot go inside and sense. That's just a lot of sensing. And also, right now we're doing the sensing because these goals are bonuses. We're saying that you get reward for actually reporting a human, okay? But what if you flip it? What if you actually say there may be a monster behind each room, right? Now that's actually, you're making your planner create all sorts of runtime monsters now, okay? So this is not really the optimistic assumption, even though it works and it's a good first step, it's not necessarily what we want to do. Instead, what we want to do is consider what is the actual unknown in this scenario, okay? The actual unknown is that your initial state is not completely specified, and the presence of the object that you're trying to sense, so the wounded person in this case, that's not completely known, okay? So one possible approach is to assume a probability distribution on this, okay, on the presence of objects of interest in the world. And once you do that, you can now balance the sensing cost. So the net benefit that I was talking about, the partial satisfaction planning, you can balance sensing cost on the one hand, that remains the same. The cost of sensing in a room remains the same. You can balance that now against the expected reward, okay? Rather than just assuming that there are people everywhere, you can have an expectation based on your probability and the reward of reporting a person. And so the approach that I propose to do for this, or that I propose to implement for this, is this idea known as conditional goals. So just a quick definition, conditional goals, a conditional goal is essentially given ground atoms A and B. Hard conditional goal A to B is defined as the requirement that if this condition A, right, if this atom A is known to be true in your initial state, then your plan must achieve condition B in the final state. Okay, so that's a conditional goal. There's a condition that's true in the initial state, then B must be achieved in the final state. Okay, and you can relax this notion a little bit. So you can define what are known as soft conditional goals. Okay, so you can now say that if A is known to be true in the initial state, okay, then any plan that makes B true in the final state, okay, it'll get a reward of U units, a utility of U units if you make B true. And you will be penalized P units if you don't make B true, okay? So that's a slightly more relaxed notion of a conditional goal. You're no longer saying that your plan has to satisfy B at the end. You're saying that if it does that, it might get some reward, okay? So that's a soft conditional goal. And a general solution using these conditional goals then is to use a distribution psi on the initial truth values of the antecedents, okay? So if you have a set of n conditional goals, okay, you have n of these conditions A1 through AN, okay, and you may have a distribution on the how A1 through AN are distributed. So you can think of A1 through AN as the actual presence of wounded people in rooms, okay? And if you have a distribution, then you can compute the optimal set of goals to be pursued, okay? So given this distribution, what is the set that maximizes my expected reward, okay? So that's the anticipated approach that I want to implement. We actually detail this a little bit in the journal paper mentioned here. I actually want to take this forward and implement this on the planner. So in a schematic form, basically what this is saying is you have conditional goals that come in, and if your initial state is fully observable, then you can observe all of the conditions associated with that conditional goal. So then it's a straightforward compilation approach. If they are hard conditional goals, you just use classical planning to solve it. If they're soft conditional goals, you use partial satisfaction planning, okay? The complexity occurs when your initial state is not fully observable, okay? So you can no longer now fully observe the antecedents. You can no longer fully observe if A1 through AN are true. So in that case, if they're hard goals, then you have no other way but to sense in every room, okay? It's almost like saying, I have n hard conditional goals, so you must sense if there is a person or not, okay? And if there is a person, you must report because this is a hard goal, okay? If they're soft goals, then you have to decide which goals you want to pursue, okay? So right now what we're doing is we're using this naive optimistic approach for the implemented system, okay? That's the OWQG that I was just talking about, okay? But there is also a slightly better approach. You can use sampling approaches given a probability distribution, and this is what I propose to do for this part. Okay, so that was about open world quantified goals. Really quickly, I will detail two smaller parts of the work. First one about model updates, and then some anticipated work about belief modeling. And I'm going to go really quickly through this. So the question again is why support model updates, right? So the key observation that we need to think about here is that there's one ground truth model of the way the world works, okay? There's one ground truth model of the domain physics, and neither the human nor the robot have this model with them, okay? The human may have some additional knowledge about how the world works just by, dint of experience or whatever that is, but it's very hard for either the human or the robot to have this complete model specified to them. And the crux of this problem is that the hard thing about models is it's impossible to specify everything up front, okay? But during execution, when your robot is actually executing in the world, you might have new information coming in. So the human might realize once he or she sees the robot doing a certain thing or not doing a certain thing, they might realize that here's some new things that the robot can do. So in specific, when you're talking about the model of the domain dynamics, you can have things like action addition. So we just saw an example of that, where the human sees a closed door, but the human knows the robot can push that door. So they need to specify that information to the robot while the architecture is executing. You can have deletion. So for example, the robot has an action that can take a picture, right? But there might be some dangerous vapors in the building that it's gone into. So you don't necessarily want to use the camera module. So you might want to tell the robot, you can no longer do that now, okay? And you can also have modification of actions and so on. So in this part, we're going to talk about model revision. So the model that we use in the planning process, the model that we use for the planning is represented in PDDL. This is the planning domain description language. And the reason we use PDDL is PDDL is quite expressive. It allows you to express a lot of features that you find in the real world, okay? So things like time, action cost, functions and things like that. And the other reason, of course, is that most of the planning community actually uses PDDL and PDDL planners, so that opens up a lot of planning techniques to us. So we use PDDL for that. And so a PDDL domain model essentially consists of these 4 sets. So you have a set of objects, set of object types. So in the example that I was talking about, your types might be, room, person, hallway, and so on. So these are your sets of object types. You have a set of logical predicates. So these describe the state of the world, okay? These describe the world of the planner. So predicates might be, at a particular room, or 2 locations are connected, or that a person is in a room, and so on. These are logical predicates. You have a set of functions. So functions can be things like action cost, okay? You can say that the cost of this action is a function of how much time, of how much distance you have to go in order to complete this action, and so on. And finally, you have A, which is a set of actions or operators. And obviously, you need actions. These are the things that the planner is creating plans out of. And these are the things that the architecture will end up executing. And revision should essentially support modification to any of these on the fly, okay? But in this work, currently, we talk only about modifying actions, okay? And in specific, we talk about adding actions to the current model, okay? So again, one way is to pause execution of the current plan. Same thing as the previous one. The architecture, architecture continues, but then the planner actually tries to replan. You provide a way of updating the existing model. So currently, like I said, we have restricted this only to action addition. And what you want to do is what I ended up doing for a solution here is I provided an API into the planner for the architecture, okay? So the architecture can essentially reach in and modify, it can reach in and set some of these parameters that are associated with an action. So some of these parameters are obviously the cost of an action, the duration, the variables that are used in that action. So for example, if you had a move action, the variables would be the location that you're at currently and the location that you are going to be at after the move action. You have the preconditions and then you have the effects. And so I provided the architecture with an API in order to use all of these to create a new action. And then once you have this new model, once you have the model with the action added in, the planner goes ahead and replans. So it creates a new plan. It gets rid of the old plan that it had, and it creates a new plan, and it sends that new plan to the architecture, to the executor to execute. So an example of action addition, and one of the key things that I want you to note here is that we actually enable the addition of actions via natural language, okay? Now, a lot of that work obviously is on the architecture side. So this is joint work with Rage Cantrell, and Rage in fact took care of the natural language side. So if you have a statement like this.
To go into a room when you are at a closed door, push it 1 meter.
So this is essentially the human specifying to the architecture that in order to go into a closed room, here's what you need to do, okay? And the natural language will pass this down into the following things. So the precondition is that you're at a closed door. The definition of the action, you can use it for the name, is that you push it. And the effect is that you are in that room, okay? And so the natural language module takes care of the following problems. It does reference resolution, parsing, background knowledge, and then finally it submits the action to the planner. So up until here, there is no real planning involved. You just submit the action to the planner. But then you need to have a solution. How are you going to accept that action gracefully? So that's where the APIs that I was talking about come in. And then here's the form of the new action. Here's how, once the action is submitted to the planner, here's how it looks in the PDDL. And in fact, this is almost the same action that we used in the real scenario. So you have this new action where some components are coming from the natural language. So the label of the action, the parameters that are being used in that action, so the door, the locations, and so on, and also the condition as well as the effect. So in order to push, you need to be at the location you are in, and you will eventually end up being inside that room. And there's also some background knowledge which is embedded in the architecture that's used to specify this action. So for example, that in order to go from one location to another, they need to be connected at all times. That's background knowledge. Also the fact that if you go from one location to another, you are no longer in the old location. That's background knowledge as well. And so this is an action that's given to the planner, and we run the planner again and create a new plan. So that's just how it works, like the approach just works. Okay, so really quickly, I'm going to talk about this work that we have just started thinking about that I'm actually quite excited about. So this is the idea of belief modeling, okay? And more specifically, can we use belief models to enhance the planning capabilities of the system? So the key idea here is that there is a restriction on the communication bandwidth in a human-robot team. Even with good natural language, there are issues between humans and robots. Humans are not necessarily always explicit either about what they're going to do or what they want to do. And so in natural teams, what you have is that agents generally have good models of each other. Okay, so if you think about a human-human team, the agents may have good models of each other, which enables them to anticipate what the other teammate may be trying to do, and it may also enable them to recognize the intentions of the other teammate. And this can affect the agent's planning. So we want to see if we can bring this to human-robot teaming, to the planner that controls the robot. So one example here is basically you have this slightly complex map. You have the robot meeting a human in the middle of a hallway. You have various locations where you need to do triage or pick up medkits and so on. So the human essentially says, Commander X is going to perform triage at room 5. Room 5 is over here. Commander X is over here. And I need you to take a medkit to room 1. So room 1 is over here. And the robot then says, okay, I'm picking up the medkit at room 2. So there's a medkit over here. Now, the thing that I want you to note here is that the robot is actually taking the stated intention of Commander X into account, okay? And it's reasoning about its beliefs of Commander X's model. And it's coming up with the belief that, you know, Commander X, since they are here and they need to go here for triage, they are more likely than not to pick up this medkit. That's the plan of Commander X, okay? So it needs to leave that medkit free for Commander X and instead pick up the other medkit. So you're using the beliefs of that agent in order to inform the planning process on your robot. And we did, the way we implemented this is basically you have the beliefs of another agent. So say Commander X is alpha, the other agent is alpha. Then you add the beliefs. So whatever you believe to be true about alpha state, you add that to your beliefs. Similarly about the goal, so this is a goal of agent alpha, this formula phi, agent alpha wants to achieve that and it has a priority P. You add that to your model as well. And the way you map this to a planning problem is you say that the initial state of the belief problem, in the planning problem, is all of these formulae such that Commander X or alpha believes in this. The goals are all of the goals that the commander has, and the objects that you're going to start planning with are all of the objects that are mentioned either in I or in G. And as for the approach, all you do is you construct the planning model of the commander from background information. So it's not unreasonable to assume that you have some background information about how all of the humans in a given scenario might act. And you construct the planning problem instance using the method that I detailed in the previous slide. And you give that instance to a planner, to another instance of our planner, and you simulate the plan of that commander, okay? You simulate the plan of agent alpha, and from that simulated plan, you extract the information that is relevant to the agent's plan, to the robot's plan, okay? So in this case, you would extract the information on which medkit the commander is going to pick up, okay? And then you inform the robot's plan accordingly. You tell the robot that, you know, oh, commander is picking up the following medkit, and so the robot makes a plan to pick up the other medkit. So we've done so we actually submitted a preliminary version of this work to AMAS this year, and we did a preliminary evaluation.
Commander X is going to perform triage in room 5.
Okay.
I need you to take a medkit to room 1.
total identity of the medkit at room 2.
So this is in real time. The planner is actually planning in real time and sending information about which room the robot is going to be in, so that it can state to the agent which medkit it is actually going to pick up. So that's just the proposed approach. We are still working on this problem. So quickly, a summary of the proposed work from the 4 different sections that I went through. So if you remember, in the replanning, I said that I would do work on compilation of the replanning constraints to preferences, to plan preferences, and also on the extraction of commitments from plans. In the open world quantified goals, the proposed work is to implement the conditional goal-based general approach to handle open world quantified goals with probabilities. In the belief modeling, what still needs to be done is the full implementation and evaluation of the mapping of agent beliefs into a PDDL planning problem, and see how this can help the planning process. And finally, because I spent all this time on actually engineering the system to work first and then thought about the various issues that were involved after the engineering was completed, I actually want to collect all of this and write an article on the challenges for planning in human robot teaming, because like I said, there has been a lot of interest in this work. People have, there have been a lot of citations to different work in this area. So I actually want to collect all of this and write an article on this. So that's part of the proposed work as well. And so I'll wrap up with a summary of what I have talked about today. So planning for human robot teaming is an important problem, and I first demonstrated the successful integration of a planner into a human robot teaming architecture, and I showed that the planner is able to generate plans in real time. It is able to accept updates on various kinds of information from the world, generate new plans, all of this in real time while executing on a robot. And once that was done, I took a step back. I detailed the techniques that were used for the integration, and then for some of them, I actually did further analysis, and I showed some novel extensions that can be made. And these were the 4 techniques that I talked about. And I also listed the tasks that need to be completed for the completion of this thesis. So that's what I had today. Thank you, and I'll take questions.
Okay, so I think right now the floor is open for questions from anybody, and then after that we'll then just the committee answer questions.
Yes.
So this last part, the belief modeling for the other agents. It seems to me that you're treading perilously close here to having to do plan recognition.
Yes.
Kartik, I cannot hear a single word of what other people are saying other than you. I'm just telling you.
Oh, sorry. Let me see if we can do. So the mic is there.
No, you can just probably, yeah.
Well, maybe you should worry about it.
I can repeat the question. I'll repeat the question. Okay.
So for example here, if you inferred that the other guy was going to go get the med kit out of room 5, and then you planned to go get the med kit out of room 2, and you communicated that fact, and he said, "Oh, I was going to get the med kit out of room 2." Right. So now what do you do?
Right.
Or if instead you get your initial model, but you observe him coming out of the room and going
the other
towards,
direction. Yeah.
Right now you've got a case where you've actually observed some of his actions, and you now have a plan recognition problem to figure out which room he's going to go to.
Right. So Matthias, the question that Dave was asking is that the belief modeling work that I was detailing, it seems very close to plan recognition methods, and it seems like you might have to actually use plan recognition given some facts. For example, if you observe some actions of the commander, there might actually be a plan recognition problem here. So yes, actually, Rao and I were speaking about this as well, that this eventually, I think we want to turn this into a plan recognition problem as well as a goal recognition problem, because there are also intents that are being stated, right? So you want to recognize the goals that a particular commander is trying to achieve. So yeah, I mean, to answer your question, I think it is very close to plan recognition, and part of the proposed work. So like I said, we submitted a version of this to AMAS, but I actually want to bring in more of a plan recognition approach into this problem and see if we can make it work, for example, with the architecture. Will it still be fast enough to act in real time? And I want to write about that. So yeah, there is plan recognition involved in this.
It is actually more general than plan recognition. because in plan recognition you assume that you have gotten some information about partial set of actions that have been done, and then you're trying to figure out what is the rest of the plan. Here it's sort of plan ascription. I mean, you're basically, he's making the assumption that I know how commander thinks, and I will ascribe the following plan to him.
Right.
And then of course, as you said, on top of it, if in fact my ascription doesn't work, then I have to change.
Change that.
Okay. So it's sort of pre-planned recognition, because
So
before even, you could wait until where the commander is going to figure out where you are going.
Right.
But here, the part that he showed is really
right. So that happens because we are assuming that we have a background theory of the commander's model, and we're assuming that the commander is going to use that model to conduct their planning. So that's how, for example, I'm able to say that the commander will pick up the medkit in room 5. Now I agree that background theory may not be complete. There may be other aspects to it. It may also be incorrect, right? In that case, you actually need to go further down into plan recognition and see that, oh, these observations now no longer tally with the model that I had. So you might even do things like model update, for example. So I think recently there's been work in our group on, if you have enough cases, right? You observe enough plan traces, can you actually update an incorrect or incomplete model based on those plan traces? So there are extensions that you can make with that.
So I don't know if you're familiar with the plan recognition work of Ramirez and Gaffner.
Right, the compilation, yeah.
So that, it seems to me that approach works just fine if you haven't observed any actions whatsoever.
no.
Right? It's just assuming that the agent is acting in the most rational fashion, namely that it's going after.
So that
optimal
approach
plan.
also assumes that agent's model
That
is
the model,
completely
yeah.
known, right?
Yes.
Yeah,
So in that particular case, you assume that you know both the agent's model. I mean, I think, yeah, so the entire model, Gaffner and Ramirez assume that the entire model of the agent is known, and some observations may or may not have been given, in which case you're finding the plan that's most consistent. Yeah, I see what your point. Okay.
yes.
Can I ask you a question?
Go ahead, yes.
I only have 2 questions really. The first one is on the replanning part.
Okay.
That is, anything that has to do with the planner replanning, because the planner is dormant, doesn't itself monitor and depends on state updates sent from the architecture,
Right.
will run into the following problem. If the robot's continuing to execute an action as it is when it executes a plan, and a state update is triggered from any of the sensors, say, because we're looking out for things like doorways or people or what have you. The difficulty can arise that the planner is getting the update and is replanning while the action is going on.
Right.
Your solution was to plan fast and send the plan back, but that's not a good solution, right? Because there are cases where you don't want to continue the current action. In fact, you want to stop the current action
As soon as possible.
But it's not as simple as stopping the current action either. If you're a UAV and you're flying, you cannot just not fly, right? You have to go somewhere. So how would you handle that?
So one way of handling this is to give the planner some additional knowledge, for example. So you could annotate, so the action model that you give to the planner right now, right? You could annotate the actions that are given to the planner with some additional conditions, okay? So this is the way, so for example, if you have plan validity conditions, for example, okay? So there's been work in the planning community on, here's a plan, and in case you have to replan, here are some conditions that need to be upheld, okay, at all times. So you could, for example, put in those kinds of conditions. So for example, if you were talking about the UAV scenario, right? So you could have the action, I don't know, continue flying or something, right? But then you would also have conditions associated with it which say that at no time must the planner's trajectory be pointing more than so many angles downward.
We're not talking about the planner here, right? What you're dealing with is the action execution component.
Okay. Okay, no, okay, all right. My response was actually much more related to what you could do to the planner.
No, you have to do something to the planner, clearly, right? But you're not solving it by telling the planner what the constraints are when the action execution component is
executing
an action.
No. So I think what I was trying to say was you're trying to solve it from the planner's end by saying that here are the conditions. So the planner puts in additional plans, additional actions in the plan that ensure a smooth transition, so to say. Do you see what I'm saying? So
suppose you drive by, which is a problem we had, right? Suppose you drive by a doorway, you notice the doorway, and you update the planner and you want to form a plan to go in. By the time the plan comes back, the doorway is not perceived by the robot anymore.
Okay.
How would you handle that?
Right. So on the execution side, I think that could be handled, for example, by storing. If you had
I'm asking you, how would you handle that from the planner side, in conjunction with the execution side? What could you do?
So let's see.
The planner gets the state update, right?
Right.
You might know something ahead of time. For example, you might know that when you see doorways, because you're construing a plan, right, to go in, that you want to go in there.
Right.
You might have general knowledge about the doorway being transient perception, right?
Right.
So the same way that the planner constructs conditional observations, right? Maybe you have to construct conditional actions that immediately get executed in response.
Okay. Yeah, I mean there is right. So there is a notion of I think reactive planning. So in fact, I was looking at some of this work because of things that Chitta pointed out. So Chitta was pointing out this whole reactive agents versus deliberative agents, right? So in a sense, we can think of our planning and our agent as having both deliberative as well as reactive components, right? So if I understand correctly, I guess what you're suggesting is more of a reactive side. So you could have reactive rules. So in addition to the deliberative rules that are there on the planner, you could have reactive rules on the agent that fire when you see a particular thing. Is that?
But they would come from the planner. The planner would sort of compile them, right? It's not that the agent has them necessarily. The planner would plan for them.
Okay. Right.
So,
and it would have to be the planner, because for any finite small number of reactive rules, I can give you a scenario where those rules won't apply, but where you would need a rule.
Right.
So Matthias, I think he is of the age when he never had to ask for directions while driving.
I'm sorry, I couldn't hear you.
Oh no. So Chitta was talking about the parallel to asking for directions while driving.
I think he never asked directions while driving because he used the
GPS.
GPS. So you predict where you're going. So the person who is finding directions for you will predict where you're going, and then say, okay, you'll pass this and from there.
Right, but I mean, I understand that, but I guess on the planning side, you could have, for example, conditional plans. You could make conditional plans before time. So, for example, if you take the driving example, I guess that's what people used to do before they had GPSs that planned the entire thing for them. That you could make a conditional plan that you could say, if I don't know what to do in a given thing, here are possible ways to react. And so, if the world turned out not to be the way you thought it would be, so suppose some on-ramp onto a freeway was closed, then you have a conditional plan to take some other freeway to go across the state or to go to the next exit and then continue evaluating that. So I think that would be a planning thing that you could do, and there are conditional planning methods that can be used. Not in SAP Replan right now, we don't have that implemented, but we could certainly add that capability, I think. Okay,
good. The other question is the question about the extensionally quantified open world code that I sent you before.
Yes.
In your solution to it, you did a type restriction.
Yes.
And kept it a universally quantified code, but that's clearly not what we want.
Yes.
Right? Yes. Because the big difference is, in one case, it's literally, as the universal quantifier is cast in first order logic, it's a conditional statement. For all x, if there is such a thing, then.
Yes.
With the existentially quantified code, it's not like that. Yet there's still a conditional in a sense there, right? Because you cannot do it unless there's such a thing.
Right. Yes.
So type restriction is not going to do it.
No, I agree. Yes. Go ahead. Oh, okay. Yeah, I agree that type restriction it's basically just a gross approximation to what you perhaps actually need to be doing for that. So one, let's see. I'm trying to think of a general enough solution that might work for planning.
Type restriction basically allows you to populate the whole environment with a whole bunch of pseudo objects, right? In the way you do it.
Yes, yes, so yes.
And that's not okay for existential.
That's, yeah, you shouldn't be able to do that for an existential group.
I shouldn't have in any possible room a medkit, for example. If
yes,
if
it's a specific room.
I want to get that one.
Yes.
Right. So in your solution to his question, you did the type restriction to end rooms, right? And if there's more than one end room, then once the robot finds the med kit in one end room, it won't stop.
It will actually go
into the other end rooms.
Right.
More generally, if the statement is there is a med kit in one of the rooms, after the robot finds one, it won't stop.
It won't stop if there's more than one. Yeah. Right. It's true. So,
I mean, you don't have to stop. Right, to get it. I think that's an interesting question that should be on the to-do list, because I don't think the current solution is a solution.
I'm sorry, can you repeat that? You cut out.
Sorry, I'm not expecting you to have a solution right now. All I'm saying is that may be something that you want to put on your to-do list.
Okay.
Because the current solution is not a solution.
Yes, I agree that the current solution is not a solution. In fact, I think after I added that piece in as the answer to your question, I had a discussion with Rao, and Rao was also pointing out that this is not a solution. It's just the way we handle it right now, and it will break down very easily because, like Dave said, if you have more than one end room. So yeah, I think I will put that on the list of things to be considered.
Okay, I'm done. Very good.
I think that can be handled with your more general conditional goal mechanism, right? So I think it's possible for you to do existential things right in that formalism.
Okay, so let's see. So if I have, no, but wouldn't that still be saying, so if I said there is, oh, that's right, okay. So I could, instead of saying this is on an object type, I could name a specific object. So I could say that instead of saying that if you, so for a given room, here is the goal associated with that room, I could say that for this specific room, here's a specific conditional goal associated with that.
What you want to be able to say, for example, is if there is a med kit in one of the rooms, then take it to room, then my goal is to take it to this other room.
Okay, yeah.
Right? And that's an existential statement, right? It's an existential conditional statement.
Right. Yeah, so the point I'm making is that the antecedent of your conditional statement then, right? The statement A, yeah, it would be an existential, okay, yeah. That's a possible approach, yeah. I think I'll try to develop that further. So Matthias, what Dave was saying was essentially you could use the conditional goals that I was talking about, the more general way of representing open world quantified goals, and your antecedent of the condition, that could now be an existential quantifier, and that's one possible way in which you could handle the existential goal.
Other open forum questions?
So at the core of the planning, you use a SAPA replan?
Yes. Yeah, we use.
So that's kind of, that's not your work, or that's...
So SAPA replan, so the history of that is that SAPA replan builds on the SAPA temporal planner. That is Mindo's work. So Mindo made the SAPA temporal planner. Will Cushing actually implemented the replanning updates part of SAPA replan. So the updates themselves, that's not my work. But then I implemented the OWQG part, the open world quantified goals.
So the big system is called SAPA replan.
Yeah, I mean the planning system is called SAPA replan. All of what I said is in SAPA replan. Everything is in, all four are part of SAPA replan, yes.
And are there other like HRI work where plans are used?
In human-robot interaction, you mean? Yeah, there has been so even in the planning community, for example, there has been work. So one thing that I mentioned in the in my proposal document, as well as the answers to the comprehensive, there's been work on, for example, generating excuses and explanations. Okay, so when you have human-robot teams and there is a task that your robot cannot achieve now, okay, is there, instead of just failing and saying I'm not able to do this task, can it actually come up with an explanation as to why it was not able to achieve that task? And tell the human that, in the hope that the human might give it some more information. Okay, so there has been work on using planning to generate those excuses. So in general, I think there's been a bit of work on
like similarity, like use of planners.
Yeah, so there's been work, so I can give you examples. So in fact, I had some slides about this. So for example, when I was talking about updating domain descriptions, right, there's been work by Eiter et al. In 2010 where they were talking about a formal logic for actually specifying action updates and how to assimilate those action updates. And that was also in the context of, for example, if you have an agent's domain model that's changing constantly. There's been, let's see. So yeah, I mean, there are a
lot of theoretical kind of things.
Right.
I'm just thinking.
But on a specific robotic system. So the only things I can think of, for example, is the excuses thing. I know they evaluated it on a robotic system, but I think ours is one of the first work to use planning with an implemented system where the planner is planning in real time, rather than just saying, here are some guarantees, but we have not evaluated on a system. A lot of systems do that, like you pointed out, but ours, as far as I know, it's one of the only systems where a planner is used on a real system.
I have to run very soon, so
okay.
My question is if this is there anything else that's required on my end?
I think, one second, just give me a second. Are there any